Hello. Today I want to present you a new sparse linear regression approach and its application to the fMRI analysis. You can find me also at my poster. I would be happy to talk to you. We all know that fMRI bolt signal is very useful for scientific and clinical purposes, but imagine that you want to analyze an experiment with no predefined response times. It can be, for example, the low-frequency fluctuation in the resting state, or the natural viewing or audio experiment. Or you compute the connectivity and maybe you want to interpret it. The common challenge of all these tasks is that the measured bolt signal is not directly the neuronal activity. But let's see what we can do about it. Instead of the neuronal activity directly, the fMRI bolt measures the change in blood flow driven by the metabolic demands of neurons. We can model the bolt signal by convolution the hemodynamic response function with a neuronal signal. Here, the red lines are neuronal activations, the blue one is modeled bolt signal generated from it. In the mathematical terms, the measured signal Y can be modeled as a convolution of neuronal signal S with the kernel H with adding some noise. Or we can rewrite it in a linear regression form where Y is measured, H is known and based on the hemodynamic response, epsilon is noise, and S is a neuronal activity that should be estimated. Estimation of S in this task is called the deconvolution. It is important to mention here that in many applications, people expect the vector of activations to be sparse. So we start from the measured bolt signal, and our goal is to estimate the neuronal activity S. As this task can be rewritten in a linear regression form, where we assume that regressor's matrix is known, we can apply the OLS approach. However, for this type of data, OLS estimate is extremely noisy and not useful in practice. Thus, the paradigm-free mapping based on the sparse approaches was proposed by Caballero-Gaudes. The main idea is to apply the sparse linear regression method, for example, LASSO. Here, instead of only minimizing the residuals of our model as in standard OLS approach, we add an additional term which is responsible for the solution sparsity. Practically, we have a set of two solutions that are dependent on the regularization parameter lambda. Many different sparsity levels are possible from full to the trivial signal, and we need to select the best solution. Alternative methods can be used instead of LASSO, such as, for example, Dantzig selector. However, the main idea stays the same, and the optimal lambda should be selected. Usually, the standard instruments such as Akaike or bias information criteria are used for that. However, applied to the region-level signal, those methods do not perform well. So, in this work, we introduce the alternative approach that uses both OLS and sparse approaches and does not require an application of the information criteria. In our approach, we assume that activations in the OLS estimate come from two classes, true activations and noise. Then the naive bias classifier can be used to distinguish them. However, it requires the knowledge of priors and distributions of classes. We don't know the ground truth, but can estimate the priors and distributions using the OLS estimate itself and the set of sparse solutions. For that, Gaussian mixture model can be used. But we propose to use the much more flexible model of mixture with varying concentrations. Unlike in the Gaussian mixture model, here we allow every peak to have its own probability to belong to one or another class. This means that different peaks will have a different probability to be a true activation. All what we need to have for that are these probabilities. We can estimate them from the set of sparse solutions. The more the peak is present in the set of sparse solutions, the higher chance that it's a true activation. Then, as was already mentioned, we estimate the distribution of classes and run the naive Bayes classifier. Now I would like to show you the results of the mentioned method on the real data. We ran the experiment where volunteers were pressing the button. It was a working memory task. However, now we are not interested in memory, but in a motor activity. From the measurements, we extracted the primary motor cortex times US and used it to estimate the neuronal activity. Then this estimated signal was compared to the button presses, which we took as a ground truth of the motor cortex activation. Ideally, we would detect all the button presses, but not more than that. We ran the deconvolution on the group signal and compared the results with the ground truth. The result you can see on this picture. The convolved black peaks should correspond to the red peaks that mark button presses. Here, the deconvolution result was quite good and much better than the standard approaches, as you can see from the table in the top right corner of the slide. We also looked at the subject level results. Here are true and false positive rate for the proposed method and several standard techniques. The optimal point at this graph would be the top left corner, all true peaks detected and no false activations. Result of the proposed method are shown in red, and this cloud is closer to the optimal point than clouds for standard methods. So the main conclusion stays the same. Even though the result is not perfect, the proposed method works better than random and better than the standard approaches. Here, I would like to point out that the deconvolution of BOLD is a particular application, but not the only one possible. The proposed approach or ideas can be useful in a wider range of tasks, in neuroimaging, or even more general ones. I don't want to be too strong and say that while working with fMRI BOLD signal, you always need to estimate the underlying neuronal activity. That's not true. However, just think, maybe your research results and interpretability would benefit from the deconvolution. Or maybe you are not working with BOLD, but still the deconvolution or more general sparse method can be useful for your result. The main idea of the proposed method is to split activations into true activations and noise. And technically, it can be done through the model of mixtures with varying concentrations. You can find the paper online at this link. And with this, I would like to thank my collaborators and you for your attention.